Welcome back, everybody. Mr. Renneker here yet again. Today we are going to focus on 3D objects in the real world. And your main objectives for today are going to be to apply concepts of both surface area and volume to solve some real world problems, which we're going to see some examples of here next. Let's go ahead and get started. In our first problem, it says the outsides of purple traps are coated with glue to catch emerald ash borers. Just as a side note, emerald ash borers are a type of insect that they're trying to catch with these glue traps, so you understand what's going on. Next, it says you make your own trap in the shape of a rectangular prism with an open top and bottom, which will be an extra little side piece of information we need to refer to. Our question is simply, what is the surface area that you need to coat with glue? So we do know we have a rectangular prism, which I'm going to go ahead and sketch here. And we know we're covering the outside of that prism with some glue. So perhaps I have some over here and have some over here and some other sides we can't see, of course. It does mention that there's an open top and bottom, which basically means that this surface here and the one that we can't see underneath, they actually don't exist. There's nothing there for me to put glue on. So it says, what's the surface area that you need to coat with glue? So what I want to keep in mind is I have this front face here. Keep in mind that there is a back as well. We just can't see it. It's kind of hidden behind here. We have this right side we talked about coating with glue, and if there's a right, there's also this left side over here that we can't see. So all in all, I have one, two, three, I've got four surfaces. But if you remember our work earlier with surface area of a rectangular prism, we would have actually found the area of 6 surfaces. But here we're only going to count 4, again, because we're not counting the top and the bottom. They don't actually exist. So when we talked about calculating surface area, we were actually able to use the dimensions, and we'd pair up numbers like length and width and height and so on. So we're just going to be a little bit more intentional about which numbers or dimensions we're actually using, since we don't actually have to use all of the combinations, again, because the top and bottom don't exist. So here's the actual trap, or an image of the actual trap that they're discussing. And it also helps us see all of the dimensions here. And I know then that I'm going to have to find the area of the front, but the back as well. So when I think about finding the front, well, that require me to take the length here, 12 inches, times the height of the prism, which is 20 inches. So to find that surface area, I am going to take length times height. But since I have a front and back, I will go ahead and multiply that by 2 as well. So that'll give me the areas of the front and back. I'm going to need to add the other ones though. The other sides here, I've got this right-hand side that we had talked about earlier. And to find that area, I'm going to have to take the width times the height. So I'm going to go ahead and take width times height. That would get me the right-hand side. But to have the left as well, we'll go ahead and multiply that by 2. And we're going to use this kind of idea to help us find the actual surface area in question. Again, if we had been doing total surface area, we would have added a whole nother section on here for the top and bottom. It's just not necessary for us in this application style problem. We'll go ahead and substitute in our numbers. We have 2 times the length is 12 times the height is 20, plus 2 times the width, which is 10, and the height, which is still 20. And it's this kind of situation where we just have to be very intentional about what the problem is telling us, what we actually need to use. Do we need just the regular formula, if you will, or do we need to pick and choose the pieces that we need? So for the front and back, we should end up with 480 square inches. And then for the right and left, we should end up with another 400 square inches. And all in all, then it says, what's the surface area that you need to coat with glue? Take 480 plus 400. And you should end up with 880 square inches. Our next problem is going to ask us to focus on the surface area of pyramids, which we saw earlier. So it says a roof, which you can see here, is shaped like a square pyramid. It says one bundle of shingles. Shingles are those flat, grayish, black, red, whatever color they're made of, tiles that people put on their roofs. One bundle of these covers 25 square feet. So how many bundles should you buy to cover the entire roof? And the only way we're going to be able to answer that question, ladies and gentlemen, is to find the total surface area of the roof, and then we'll see how many bundles it takes for us to get there. So when we look at the roof here, we can obviously see this pyramid-esque structure at the top here. But the part that we're going to have to be careful with this time is, normally for a pyramid, if we looked at the net, you'd have the square for the base, and then you'd have a bunch of triangles on all the sides to make the lateral faces. The issue with this one is, while this is still a square pyramid, the base right here, the square, that would be underneath the roof here and would not get covered with shingles. Shingles only go on the top of the roof. At no point are they placed underneath or at any other locations, which means that the base shouldn't be counted. It means all I really care about are these 4 lateral faces. And thankfully, since our pyramids have been regular at this point, all 4 of the lateral faces will be identical. So we really only have to find the area of one of these faces, and we'll multiply it by 4 to find all of them, and that'll help us go a long way with this problem. So let's start that kind of idea. So to find the area of one lateral face, which is a triangle, we would have to take 1/2 of that surface's base times its height. And it does look like from the image that the base here is 18 feet, so we have 1/2 times 18 times the height of that face, which is also told to us it's 15 feet. And again, that'll help us find one lateral face. So we have 1/2 times 18, which is 9, and 9 times 15, which should be 135 square feet. But again, that's just the one lateral face we tried to find. We have 4 of them, so we're going to go ahead and take that value times 4, and we should have the total surface area of the roof. Now again, that won't answer my the final question being asked here, but it will go a long way. So we'll take 4 times 135, and you should end up with 540 square feet. So that's the total surface area of the roof that will be covered in shingles. When we go back to read the problem, it says that one bundle of shingles covers 25 square feet. So how many of those bundles do we need to actually cover the roof? So we could simply start to count up 25, 25, 25, start to count up how many of those groups do we need. But that could take a while and be really tedious and isn't necessary here. So we can use one of 2 ideas. I'm going to use a little bit of algebra though. I'm going to say, okay, I get bundles of 25 times however many I need, and how many of those will I actually need that'll get me to 540. So I can use this idea to actually solve a little one-step equation and isolate the variable. I'll go ahead and divide by that 25, which may have been what some of you are ready to try anyway. And when you divide this one, you're actually going to see that you get an interesting number. It's going to tell us that, hey, you actually need 21.6 bundles of shingles. Now, mathematically, that's correct. However, in a real world application, you can't exactly walk into a roofing store or a hardware store or something and go up and put 21 bundles in your cart and then rip open the extra one to only put this part of the bundle inside of it. So what are we actually going to have to do? Well, I can't buy part of that bundle. So we're actually going to have to say that we're going to have to round up and buy 22 bundles of shingles, and we'll have a little bit extra left over. In our last example, we're going to take a look at a real-life application. We're actually going to see both volume and surface area. So it says a movie theater designs 2 bags, meaning bags of popcorn, to hold 96 cubic inches of popcorn. So that's the first thing. Both of these bags have the exact same volume. I know it's volume because it's measured in cubic inches, whereas surface area would have been measured in square inches. So first thing they ask us to do for part A is find the height of each bag. So how are we going to do that? How are we going to use what we know? Well, for part A, I know that I can find volume of a prism like this, which is what they are. They're examples of rectangular prisms, by taking the area of the base times the height of the prism. Over here, they're asking us to find this height, meaning obviously, and you can see this in both pictures here, we don't have that information, which means we have to have or be able to find both of the other things, both volume and the area of the base. Well, as we mentioned from reading the problem, we already knew the volume. Both of these have a volume of 96 cubic inches, which means if we take that volume and substitute it in here, we should be one step closer to being able to find our missing heights. Now, if we look at bag A first, I'm going to have to find the area of the base by realizing that the area of the base down here is actually a rectangle. So I can find its area by multiplying these two dimensions together. And 3 times 4 would give me an area of 12 square inches. Normally we would take that area times the height, but of course we don't have it. That's what we're looking for, which means that here we could simply solve this equation since 12 times h would equal 96. So we're just going to take 96 and divide it by 12, and we'll do that algebraically, treating this like an equation. Of course, 12 divided by 12 is 1 times h, which is just h, and 96 divided by 12, that should leave us with a height of 8 inches. So for bag A, I have a height of 8 inches, and that's the first part of our work. But we're going to do the same thing again, this time though for bag B, because they want us to find the height of each bag. So we'll take the 96 cubic inches for the volume, and we'll have to find this area again. Notice that this base is actually a square. It's a 4 by 4 inch square, which means it's got an area of 4 times 4, or 16 square inches. So we can finish solving here. We'll just divide by 16, and the height, or the missing height, of bag B should be 6 inches. So we've got both missing heights here, just like part A asked for. We got 8 inches and we have 6 inches. But then what they ask us to do with that information is say, which bag should the theater choose to reduce the amount of paper needed? This is actually a really popular production question to ask. Lots of companies think of different ways to package their product, whether it's popcorn or toys or whatever else it is. And the reality is that the cardboard used, or the plastic used to package things, that costs money. On top of that, if it's cardboard or other materials, they usually print images or ads or something on that cardboard, and the ink used for that costs money. So sometimes they'll explore ways to save money by using less of those materials. So that's what they want us to know here. Which one would need the least amount of paper, or how can they reduce paper? Well, when we think about the paper or the cardboard around a package, we're only thinking about that outer shell. So when we're thinking about the outer shell, or what we would sometimes call the outer boundary, we're actually asking to find the surface area of each one of these bags. So that's what we're going to do for part B. We're going to explore their surface areas and see which one would actually save us um, more paper in this case. So we can start by looking at the surface area of bag A, and we can start off relatively straightforward. We have a length here, we have a width, and of course we just found a height a little bit ago. And we know normally we'd pair those up, but there's just that one extra layer here to this being a real world problem that we have to keep in mind. We have a front, that means we have a back. We have a left side, that means we have a right side. We have a bottom, but notice this time we don't actually have a top. Of course, that would actually be a pretty crummy popcorn bag. You wouldn't be able to get into the popcorn that way. So when we find the surface area, we have to keep in mind that instead of counting all 6 faces of a rectangular prism, we're actually only going to count 5 here. So we can start with things like the front here, front right up here. That would require us to take length, so 2 times length times height, and then we're going to add left and the right sides. The left here is the width times the height, so 2 times width times height. But for the last part, I'm going to be a little bit cautious. I'm not going to multiply it by 2, because when I go to look at the bottom, which is length times width, I don't get to do it again for the top, as we mentioned. Past that, we're just going to go ahead and add in all our numbers. We're going to speed that up just a little bit since we've done surface area enough times. For the surface area of the front and the back, that should be our length times our height piece. We would take 4 times 8, which is 32, times 2, which would give us 64 square inches, plus, now we'll do the left and the right, that's width times height. So width is 3, height is 8, 3 times 8 is 24, times 2 gives us 48 square inches. And finally, just the bottom itself, we don't double this one again, is going to be 3 by 4, which is 12 square inches. We add everything up here, and you actually end up with 124 square inches. But that's just the surface area of bag A. We would repeat this process for B, but again, for time's sake, we're going to go ahead and speed that up because the process will be exactly the same. Front and the back, left and the right, but don't include the top, only the bottom here. Once you finish that, you'd find that bag B actually has a total surface area of 112 square inches. But again, right now, what have we done? We've explored some surface area based on some things we knew about volume. When the question says, which bag should the theater choose to reduce the amount of paper needed? Obviously here that should be bag B, because 112 square inches is less than 124. So while both bags can hold 96 cubic inches of popcorn, meaning both bags actually have the same amount of popcorn in them, bag B would save the company some paper, which means that it would be cheaper for them to produce the bags. There are plenty of other real world application problems you guys will experience here, but the overarching idea I want you guys to keep in mind is that focus on the details. What should you calculate? What should you include? And what shouldn't you? That way you don't necessarily always do too much work. As always, if you have extra questions, reach out to me via email, and otherwise, I will talk to you guys next time.